Okay, so let me so now we're gonna look at chapter 10, which deals with molecular shapes and hybridization and so on. So what I'm gonna do is hand out these to the students here. And the last time we were here, we talked about molecular shapes. I didn't get into the other related topics, but of course, I've published the videos for those topics. So I'm going to assume that you have at least viewed those videos. That should make things a bit easier in terms of answering the questions in this assignment. And for those of you out there in Zoom, let me see if I have published it. Not, I'm going to do that now.
I think you're in chemistry too.
Oh, thank you. Thank you for pointing that out. So let me go to chemistry 1. Files. So let me see here. So 6, 7, and 8 is what I said your next test will be based on, right?
Yes, is that the final?
No, the final, I'm going to announce the final date. In fact, I think the final date should be in your syllabus, but if not,
I think it is, I just want to make sure.
Yeah. because that is set by the college, the final date is set by the college, and I'm going to give you the option of either doing the final test in the testing center or coming here on the scheduled date, right? You have those two options. Okay, so I've just published the assignment keys for 6, 7, 8. All right. Okay, so with that out of the way, let me go to what we'll be doing today, which will be chapter 10, assignment 10. Okay, so let me see, let me publish this for you guys out there in Zoom. And let me open this up. And let me download it. Okay, so in this chapter, one of the things that we're going to talk about is, well, we talked about geometry already, but we're going to talk about also polarity, this whole idea of polarity and hybridization, right? So of course we know about the geometry. We talked about the different shapes depending on the Lewis structure of the molecule. And this is based on the valence shell electron pair repulsion theory, which basically says that the shape that is adopted by the molecule is as a result, or any molecule or polyatomic ion is as a result of the repulsion of electron pairs around the central atom, right? So if you have, I think the simplest one, or the first one we started off with, was a linear shape where you have a central atom. Bonded to 2 other atoms. Then basically the shape will be linear because the bonds connecting to the 2 other atoms will repel each other, so that those bonds will be as far from each other as possible. And therefore, as a result, oh gosh, nothing is going good for me today. I brought the wrong USB cord, and I don't put that another one here. Shoot. All right, anyway, I may have to go to my car for that. So basically, in the case of a linear molecule, as I said before, you have a central atom bonded to 2 other atoms, then you have the repulsion that would take place between the 2 bonds, and therefore the molecule will be linear. And we went through the different types, from the linear to the most complex one that we looked at was the octahedral. All right. So when the question is asking, give the geometry, that's basically what the question is asking for, which means that you have to determine the Lewis structure first, because the Lewis structure will give you the situation around the central atom in terms of the lone pairs and bonding pairs, all right? The polarity now has to do with, well, it's related to the shape of the molecule, but it has to do with separation of charge between two atoms, right? We talked about that already, polar bonds. But we can also extend that to the nature of the molecule being polar or not. Now, how do we determine if the molecule is polar? I'm really gonna need the USB. No, that won't work. You know what? Give me a minute. Let me just run to my car and get the USB cord. Okay.
Yeah, I get it now, it's like. Yeah. Every summer. For a class. I would like, I work for, I can't do that. Yeah, it's more than classes.
Seven classes done.
No, I did more accelerated courses last summer. I'm gonna do that again. I'm not doing it.
I have 3 signed up right now to do first part. So microeconomics, which I know will be. Comparative religions, which should be.
Those are just that should.
Yeah.
You have to say Forgo?
So,
Do you have to say Forgo? Yeah. I would say Forgo, but it's only offered in the fall here, so I'm wondering if cause that was my initial was take it over
so you can-
10-2 over the summer and then Oregon in the fall. But I can't do that much of this summer, so I'm either gonna go to Santa Fe or UCF or Union. I'm already like involved in UCF, cause I did my bachelor's through there. But, Santa Fe is closer.
Yeah.
So I don't know. which one.
Okay.
It is, they're very organized up, they would get awarded that, never had to go to the game once. I was very impressed. UF, it's like Ivy League, you know,
See,
that's what I've heard, I don't know.
heard that too. As a transfer student. right? You're like a freshman.
Yeah,
Oh,
yeah. Yeah, exactly.
okay. I'm sorry about that, folks. All right, let's see here. So. What was I saying? Okay, so I was talking about the polarity, right? So basically, if you recall, if you have two atoms like hydrogen and chlorine bonded to each other, one is more electronegative than the other. That means that this bond is polar, right? There's a separation of charge where the electrons that are being shared between the hydrogen and chlorine would be on average closer to the chlorine atom compared to the hydrogen. As a result, the chlorine will have a partial negative charge. That's what this means. This means partial negative charge. And the hydrogen will have a partial plus charge. And therefore, we say that the bond is polar. And one of the properties of polarity in a bond is that it has direction. And conventionally, we represent the direction using this symbolism here, where we have an arrow pointing from the positive to the negative, and there's a cross at the tail of that arrow, right? So this that you see me draw here represents the direction of the polarity of that bond, right? Now, we can have not only a polar bond, but also a polar molecule, all right? So what do we mean by that? Well, basically, what you do in order to determine whether or not a molecule is polar is that we take into account the magnitude and directions of all the polarities of the bonds that are within the molecule. And before I forget, there's another term that we use to define the separation of a charge. We call that a dipole, right? So whenever you see that term dipole, it means a separation of charge within a bond and also within a molecule, which is what we're going to look at shortly. So before we do any one of these, let me just do an example. I'm going to use carbon tetrachloride as an example, right? So if you go through all the steps for determining the shape of the carbon tetrachloride molecule, you'll see that the Lewis structure is C. Cl, 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 Cl. So I'm talking about carbon tetrachloride, right? And these will be the lone pairs around the chlorines.
Well, sorry, do you have the handout for this?
Oh, yeah. You're from that paper. Everybody got a copy? All right. So so this is the Lewis structure for carbon tetrachloride, right? Now, based on what we learned last class, the shape of the molecule will be tetrahedral, right? Now, if you think, and now this is where you have to kind of think of the molecule in 3 dimensions. Now, one way of drawing it, it's going to look something like this. And for those of you who apply to the organic chemistry, you're gonna see this kind of representation a whole lot, right? Basically, the wedge-shaped bond, it represents a bond that is sticking out of the plane of the board or screen. This bond here with the lines like this represents the bond that is sticking behind the plane of the screen. And these two bonds here are within the plane of the screen. All right, so that gives you a three-dimensional picture of what the molecule looks like. Now, because of the symmetry of the molecule, and also the fact that these atoms are identical, we know that because chlorine is more electronegative than carbon, you're going to have one dipole moment acting in that direction, one dipole moment acting in that direction, one dipole moment sticking out in that direction, and the fourth one will be sticking behind like that, right? And because these atoms are identical, this dipole, that dipole, and that dipole would all be equal to each other. And because of the symmetry of the molecule, they will cancel out each other, right? So because the dipoles will cancel out each other, the net dipole moment, which is another term I should have mentioned, the dipole moment is basically a way of measuring the magnitude of the dipole and the direction. The net dipole moment for this molecule will be equal to 0 because they all cancel out each other, right? And because of that, we come to the conclusion that the molecule CCl4 is nonpolar, right? The molecule is nonpolar, even though you have polar bonds within the molecule. But because of the symmetry of the distribution, and because the dipoles are all equal, then basically they'll cancel out each other, and therefore the resulting molecule would not be polar. So we say that the carbon tetrachloride molecule is nonpolar, all right? So that's the kind of idea that you're going to use to answer the polarity part of the question in assignment 10, all right? Any question about this? Any questions? Any questions? Okay, let me give another example. Let's say instead of carbon tetrachloride, you're given nitrogen trifluoride. All right. So again, if you go through all the steps to get the Lewis structure, I won't go through all of that because you guys should know how to do that by now. The Lewis structure of nitrogen trifluoride will be this. And then we have 1, 5, 6, 7, 8, 9, 10. Okay. So that would be the Lewis structure of nitrogen trifluoride. Now, in terms of the shape of the molecule, again, based on what we discussed in last class, the shape would be pyramidal. So it's going to look something like this. And you're going to have a lone pair here. All right. So you're going to have one dipole acting in this direction, one dipole acting in that direction, and the third dipole will be acting in this direction. So again, if you use your imagination, this is a trigonal pyramidal structure, right? What we will see in this case is that unlike the carbon tetrachloride example that we just looked at, in this case, the dipoles will not cancel out each other. In fact, the net dipole would be the sum of these three, and because they're all pointing down at an angle, the net dipole will be pointing down straight like this. So this would be the direction of the net dipole moment of the molecule. And therefore, we can say that the net dipole moment is a non-zero value, which means that the molecule NF3 is going to be polar. All right. So in this particular case, the dipoles do not cancel out each other, right? So therefore, overall, the molecule would have a net dipole moment, which would not be zero, would be some value, and therefore the molecule is polar. All right. So that's basically how you're going to determine the polarity of a molecule. Let me give another example, just to make sure that we are all on the same page when it comes to this topic. So if you're given, I'm gonna use a simple example this time, carbon dioxide. So the Lewis structure of carbon dioxide is this. Right? So in this particular case, this bond is polar, so you're going to have a, oh, by the way, this is linear, of course. The molecule has a linear shape, right? So in this particular case, the dipole for this carbon to oxygen bond will be acting in this direction, and the dipole for this carbon to oxygen bond will be acting in that direction, right? And because these two oxygen atoms are identical, that means that the size of this dipole would be exactly the same as the size of that dipole. And because they're linearly opposed, they're acting in opposite direction. That means that the net dipole moment is equal to 0, which means that CO2 is nonpolar. All right, and that's it. Okay. Now let me make a minor change to this carbon dioxide molecule. If instead of oxygen here, we have, let's say, sulfur, right? Question is, would this molecule be would this molecule be polar or non-polar? All right. Well, it's going to be a linear molecule, right? However, the magnitude of this dipole here would be different. I don't know if it's larger or smaller, but it would be different, right? This dipole here, acting in this direction, will be different from this dipole acting in that direction. So basically, in this particular case, the net dipole moment would be a non-zero value, right? And in that case, this molecule is going to be polar. All right. So by switching from oxygen to sulfur here, you're converting carbon dioxide, which is a nonpolar molecule, to this molecule here, where the sulfur replaces one of the oxygens, resulting in different dipoles magnitudes here and here, right? They will not be equal to each other, even though they'll be opposed, but they will not be equal to each other. And therefore, as a result, the dipole moment is a non-zero value, and therefore carbon dioxide is polar. This reminds me of a question I gave actually years ago when I was teaching organic chemistry. Let me see if I can recreate the structures involved. Let me create this here.
No, would you use the electronegativity chart to determine the non-zero value? I'm just
We
wondering.
use the electronegativity chart to determine in a bond which atom is more electronegative. So like in this bond here, the oxygen is more electronegative than the carbon. So therefore, this dipole will be acting in that direction.
Okay, I guess I'm talking in reference to the sulfur and the oxygen.
Right, same thing.
You determine- Okay.
Yeah, same thing.
Alright.
You go to the chart, you look up the values for carbon and sulfur, and again, you'll see that sulfur has a greater value, so therefore the dipole will be acting in that direction. Right, exactly. Okay, so this question I gave on my students at the time were angry with me when I gave this question. But it was really simple. I think it's because it was an organic course, and this is something that they should have learned from Chem 1. Even though I did review that topic in the organic course. But anyway, if I remember correctly, I gave them these two molecules. Right? And the question was, I think the question was something like, which one is more polar? Right? Now, basically, what they both have in common is that they have a carbon to oxygen bond, and therefore the dipole would be acting in that direction for that particular bond, right? But the difference, of course, is that you have two hydrogens here and two chlorines here, right? Now, I don't remember, I'll have to look at the values, but the carbon to hydrogen bond has a very small polarity, right? In fact, let me look up the dipole moments for okay, let me see. Okay, so Carbon is 2.5, hydrogen is 2.1, so the difference here is 0.4. That's essentially a nonpolar bond, right? So let me go back to okay, so basically, 2.5, 2.1, right? So therefore, the polarity of this bond is very small. For most purposes, will be considered to be nonpolar. Now, when we compare that to chlorine, let me see what chlorine, what's the value for chlorine? Go back here. Chlorine is 3.0, right? So here we have 2.1, 3.0, 3.0, right? So this bond has a significant polarity as well as that bond between the carbon and the two chlorines, right? So basically, in this case here, this is 2.5 as well. So therefore, nonpolar bond. So therefore, the polarity, if you compare these two and look at the net polarity based on these two, this will be relatively small, right? But between the carbon and chlorine here, that's large. So the net polarity between these two bonds would be relatively large, right? So if this is large and this is small and this is the same for carbon and oxygen, which would you expect to be the more polar molecule?
Oh, chlorine.
You sure about that? These are relatively large compared to the C to H polarity, right? These are effectively zero for most intents and purposes, right? But this remains the same. Carbon to oxygen remains the same here and here. So which you'd expect to have a net dipole moment which is smaller.
Oh, just.
Exactly. This one here would be less polar, right? Compared to this one, because the magnitude of these two are so large that they can effectively cancel out some, not all, but some of the polarity here, right? So this will be less polar and this will be more polar. And the students I had back then made the same mistake you made. They chose this as the more polar because what they looked at was just the electronegative divided, but you have to look at the bonds, how polar they are, and to what extent they will cancel out each other. All right. Okay. Enough of that. So, oh yes, ma'am.
On the table that shows us the bonds between
That shows you the.
the bonds, is that the value that you're comparing?
You're talking about the electronegative dividers. Yeah, that's the table that is posted in Canvas that you'll have access to. This right here. I think it's the last page, if I'm not mistaken. Hold on, check it. Yeah, it's the last page.
Oh, okay.
All right. Okay. So let's move on to I'm going to, if we have time, I'm going to discuss hybridization, but let's focus on the geometry and the polarity. So let me go back to here, where is it? Okay, I lost it. Okay, here it is. All right. So let's start off with selenium difluoride. Oh, somebody said something in the chat. I apologize. I keep ignoring you guys over there. He said, sorry, I missed the part where he said chapters. What chapters will be test 3? Oh, so what did I say? 6, 7, and 8, and that's for Miss Lush. Oh, and somebody did answer. Thank you, Miss Labote. All right.
Is that next week?
Yes. So right. Before you came in, I was saying that I'm going to lead the test in the testing center or testing centers next week, and it will be based on chapters 6, 7, and 8. All right.
Okay.
And I also talked about the final. I don't remember what the final date is, but it's in the syllabus. And I will provide the option of you doing the final either here during that schedule time, or if you want to do it in the testing center.
Okay,
Right.
because I was just checking the syllabus and said the final was to be established, so.
Oh, okay. I'm going to announce that because the final date is actually set by the college based on the meeting time of the class. Yes, sir. I mean, yes, I'm sorry. Okay.
With the time left, we also have a test of 9 and 10.
I'm sorry?
Will we also have a test for chapters 9 and 10?
No, that will be on the final.
Okay.
Right, exactly. So yeah, I don't want to, throw too many chapters into one regular semester exam. Yes, ma'am.
Publish a past final, so we have
I can do that right now. Let's see,
Wait, how many chapters was the final? I missed.
yeah, I'm gonna try to make the final chapter,
Bible is the.
Oh, it's just 9 and 10?
right, exactly, well, no, not the final.
Oh,
Finals gonna be a
Final is gonna be comprehensive. I'm gonna try to make it,
just meaning.
question per chapter.
So there's gonna be a fourth test and then a final?
No, third test.
It will be 9 and 10 will be on,
Okay,
but we won't have a sim.
oh, I see, okay.
Yes.
Okay, let me see here,
Syllabus, do you like press the syllabus?
okay, here's one final exam. Okay, so this is an answer key for a final exam. All right, so I'm gonna publish this one for you guys to review. That should help you to prepare for the final exam. So yes, I'm gonna try to make it a question per chapter. So since we are at the 10th chapter, that's basically, let me see if there's any other. Okay, that seems to be the only final answer key I have. I may have some more. If I remember, I'm going to publish it. I think these two are the same. Let me check something. Yeah, this will be the same thing, so I'm just going to take out this one. Okay, if there's any more that I have on a thumb drive somewhere, I'm going to, I will upload it. Okay, going back to what I was talking about. Let me see here. Where is it? No, not there. All right. Okay, so the question says, give the geometry, polarity, and hybridization. We worry about the hybridization later if we have enough time. So in the case of SEF2, you'd have to go through the same steps as we did before for getting the Lewis structure, right? So you go to the periodic table, you look up the group number for selenium, and you see that that is 6. You look up the group number of fluorine, and you see that is 7, but you have to multiply that by 2, which gives you a total of 14 for the fluorine, which gives a grand total of 20 electrons, which would equal to 10 pairs, right? And then we put the selenium in the middle, surrounded with the fluorines, put the bonding pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So that would be the Lewis structure of the selenium difluoride. So now we need to get the geometry. How do we get the geometry? If you remember, we went through the steps, the different shapes in the last class. And if you recall, if you have a central atom where it's bonded to 2 other atoms, and then it's bonded, it has 2 lone pairs on it, right? Then this is corresponding to a bent shape, right? So that means that the geometry will be bent, here, right? So that answers that question, right? Now, if it is bent, we can determine what the polarity is. Why? Because if this is the arrangement, this is a bent shape right here, right? Fluorine is more electronegative than selenium, not sulfur, right? So I just know that, but you can look at the table and you'll see that to be the case, right? So therefore, you're going to have one dipole acting in this direction, like this, another dipole acting in that direction, like that. So therefore, they will not cancel out each other. So therefore, the molecule would be polar because the net dipole moment is a non-zero value. So therefore, this would be polar. All right, because the dipoles don't cancel out each other.
It's because it's bent, right?
Yeah, because it's bent. You have the central atom here. You have one dipole acting down like this. The other one is acting down like this. So they're not canceling out each other, right? It's like, for example, it's like, think of this. Let's say you have an object here connected to 2 ropes, and one person is pulling on a rope here, and the other person is pulling on a rope here, right? That means that the object is going to be moving in that direction. It's kind of similar. Yes, ma'am.
I'm not under not quite understanding. So the two fluorines, they have the same number of electrons, they're equal across both sides, one will won't be pulling more than the other.
No, they're not pulling one than the other.
Okay,
They're pulling down
down.
like this, one like this, one like this, right?
Yes,
But they're not canceling with each other. It's not like a linear molecule where one is pulling this way and one is pulling down.
okay, because the lone pairs fall on this linear.
Yeah, exactly.
Okay,
Because of these lone pairs here, this shape will be bent.
Oh.
Right, exactly. Yes, ma'am.
We have a chart showing us the different shapes that.
I can provide that. In fact, let me see here. Hold on. Do I have that in?
It's this dipole moment, it's the same four times.
There's a chart that I had. Okay, it's not here. But I can upload it, and I'll provide it during your test, so you can determine what the shape of the molecule is based on the electron arrangement around the central atom. Okay, okay, any other questions about this? Any other questions? All right, so let's see if you can do the next one, carbon disulfide. So the first thing again we have to do is that we have to determine the Lewis structure. So how do we go about doing that?
A number of valence electrons.
Okay, so so for carbon, that's how many? 4, for sulfur, that's how many?
6 times 2.
6 times 2, which gives you 12, so that gives you a grand total of 16 electrons equal to 8 pairs. All right, and then we put the sulfur, we put the carbon in the middle, surrounded with the sulfurs, and then what?
Put your electron pairs.
I'm sorry, repeat that.
Put your electron pairs.
Okay, so of course you have to start with the bonding pairs first. 1, 2, then the non-bonding pairs, 3, 4, 5, 6, 7, 8. All right. And one thing that you should always do, which we didn't do here in the first part, is to calculate the formal charges. Right? So what would be the formal charge? How would you calculate the formal charge for carbon? Do you remember the formula for calculating the
The
formal charge?
group
The
number
group number, which is 4.
minus half the number of bonds.
All right, which is also 4. Minus what?
Minus the non-bonded.
Which is 0. So 4 minus half of 4 is plus 2. So there's going to be a plus 2 charge on this carbon. And we do the same type of calculation for the sulfur. So that would be what? 6 minus
A half a 2,
2, right? Minus
3.
6.
Oh, 6, I meant.
But it's the number of electrons, not electron pairs. All right. So it's 6 for the number of electrons, known electrons. So that gives you -1. So each of these will have -1 here and here. All right. So of course, you know what's going to happen. This is going to go down here. Unfortunately, we don't have enough space, but let me just put that out here. So S double bond, C double bond, S, and 2 lone pairs here. Okay. So that would be the Lewis structure for carbon disulfide, right? Okay. So how do we determine the geometry? What do you think the shape of this molecule is? Here we have a situation where we have the central carbon atom bonded to 2 other atoms, right? And there are no lone pairs on the central atom.
In a linear.
So
Linear.
Exactly. So linear is the shape. And what would be the polarity? Would you expect this molecule to be polar or non-polar?
No.
Pole, non-polar, I meant.
This dipole here, because of the symmetry, right? This dipole here will cancel out this dipole here, right? And these dipoles will be equal because the 2 sulfurs here are identical. So therefore, it's linear, they'll cancel out each other, and therefore the resulting molecule would be non-polar. All right, so let me just write down here. Net dipole would be equal to 0, so therefore the molecule will be non-polar. All right, and that's it. Okay, any question about this? Any questions? Any questions? All right, let me clear this. And move on to. Okay, let's look at this one here. Sulfur dioxide. So let's go through the steps again. Sulfur will contribute how many electrons? 6. Oxygen will contribute how many? 6 times 2, so that's 12. And then the grand total will be 18 electrons, which will be equal to 9 pairs. All right. So we put the sulfur in the middle, surrounded with the oxygens. So what's the next step?
Distribute the bond in pairs.
1, 2, those are the bonding pairs. Then 3, 4, 5, 6, 7, 8. We have one more pair left. 9. Right? Okay, the next step is
Formal charge.
formal charge. So let's do that for the sulfur. How do we calculate the formal charge for the sulfur?
Number, which is 6.
6 number, group number 6 minus half of
So 4,
4 minus
2.
2. So 6 minus 2 gives you plus 2 on the sulfur. And then we do the similar calculation for the oxygen, which is 6 minus half of 2 minus 6. And that gives you minus 1. So here we have minus 1 on each oxygen. So what's going to happen? You're going to have the formation of 2 double bonds here and here. Let me see if I can squeeze it in here. Double bond S, lone pair here, double bond O, 2 lone pairs here. Okay, so here we have a situation where the middle atom, the sulfur, is bonded to 2 oxygens, but it also has a lone pair on that same oxygen. I mean, on that same sulfur, right? So what do you think the shape of this molecule is going to be?
Still be better.
Bent, exactly, right? So if it is bent, so let me put here, okay, so the geometry is bent, right? We have to include that. So if it is bent, then what do you expect the polarity of the molecule to be? Would you expect it to be polar?
Oh,
Polar, exactly.
Polar.
You're going to have a dipole here. You're going to have a dipole here. They won't cancel out each other. So therefore, the net. Okay, somebody's saying something in chat. What is this person? Oh, polar. Yes, you're right, Miss Such. Okay. So the net dipole would be a non-zero value. So therefore, the molecule is going to be polar because the dipoles don't cancel out each other. All right. Any question about this one? Any question? All right. Let's look at this one. Let's see if you can do this one with very limited help from yours truly. What's the first step?
valence electrons.
Okay, so
Here's
arsenic is what?
one.
Arsenic will contribute 5 valence electrons. And what about the oxygen? 6 times 4. And then we have to take into account this, the charge. How do we do that?
You would add 3 to this.
3 electrons, exactly. So let's see what that gives. 29 plus 3, 32 electrons. 32 electrons equal to 16 pairs. Okay, next step.
Start your shape or your structure.
Okay, so what do we do now?
Distribute the pairs.
Okay, so of course you have to do the bonding pairs first, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, next step. Formal charges. Let's do the arsenic first. 5 minus half of 8 minus 0. So that gives you what? 5 minus 4 plus 1. All right. And then we do the same calculation for oxygen, which is 6 minus half of 2 minus 6. And that gives you -1. So the arsenic is going to have a +1 charge. And each oxygen is going to have a -1 charge. So what next? Okay, so basically one of these negative charges will cancel out one of these plus charges. It doesn't matter which one, so I could do this. And I'm really running out of space here, so let me write this down here. So the Lewis structure is going to be this right here. Okay, so what's the shape?
Tetrahedral?
I'm sorry?
Is it a tetrahedral?
Tetrahedral is indeed correct. That's the geometry. Okay, and I don't know if I mentioned this, but when it comes to determining the shape, it doesn't matter if the bonds are double bond, single bond, triple bond, right? That doesn't affect the shape of the molecule, all right? Okay. Okay, so polarity. Is this molecule or ion, I should say, is it polar or non-polar?
Polar?
Sure about that?
No, just guessing.
Tetrahedral, right? And remember the symmetry of the tetrahedral, it's a very symmetrical molecule, right? Or polyatomic ion, right? Remember the one that, I think the first example I worked earlier, which was carbon tetrachloride, right? Central atom surrounded by 4 other atoms, right? And we came to the conclusion that that molecule is not polar because the dipoles will cancel out each other. The same will be true for this particular structure. Even though you have negative charges here, it doesn't matter, right? It doesn't matter if you have double bonds. It doesn't matter if you have charges on the different oxygen atoms. The resulting molecule will be tetrahedral. It's going to be symmetrical, and therefore this will be non-polar.
So we're just purely looking at just the symmetry, not like number of bonds.
Right.
and Charges.
If let's say, right, if let's say I replace one of the sulfurs here, I'm sorry, if I replace one of the oxygens here with another.
Oh, yeah, okay.
Then one would not be polar, it would be non-polar, right? But because these atoms are identical,
Alright.
right, and because of the symmetrical distribution, the resulting structure would be a non-polar structure, right? Okay, any other questions about it? Any other questions? Any other questions? Okay, so I think there are 2 more structures. Let me clear this here. And scroll down. Okay, NO3 minus, which is a nitric ion. So tell me what to write down.
Do we have to do the hybridization part?
Yeah, we're gonna get to that later on. I want to make sure that you guys understand everything else, up to and include. Okay, so,
It's 5,
oh, nitrogen is 5, yeah.
6.
Oxygen is 3 times 2, which is 6. And the negative charge will contribute 1 electron, right? So that's 11 plus 1, 12 electrons, which will equal to 6 squared. Yes, ma'am.
3 times 2. Cause it's in.
Oh,
six.
what am I saying? 3 times 6. I'm confusing the valence electron with the charges. That's 18, my bad. So this is incorrect. Okay, so that's 24 electron, whoops. 24 electrons, which would equal to 12 pairs. All right. So we put the nitrogen in the middle, surrounded with the oxygens. Okay, what next?
Does it matter if when it's an uneven, if it's at the top and the bottom?
Not when you're drawing the Lewis structure. Because again, the Lewis structure is not concerned, when you're drawing the Lewis structure, you're not concerned with the shape. You're just concerned with how the atoms are connected to each other and where you put the bonding pairs or lone pairs, and that's it, right? The shape is what comes after, right? Okay, so, what next?
Distribute the pairs.
Bonding pairs first, 1, 2, 3. Then the non-bonding pairs, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So the next step is formal charges, right? So let's do so for the nitrogen. Well, how do you calculate the formal charge for the nitrogen?
5,
Group number 5 minus
half, 6,
half of 6, you're right, minus,
0.
so that gives 5 minus 3, that gives you +2. So we're gonna have a +2 here, right? And then we do the same thing for each oxygen. So that would be what?
6 minus 1 half 2
Mm-hmm.
minus 6.
-6, and that gives you -1, right? So each oxygen is going to have a -1 charge. So what's the next step?
You should be able to double onto the oxygen.
Nope, I knew somebody was gonna say that. It's one of the oxygens. We talked about this. Only one of the oxygen will donate a pair of electrons. I'm just gonna write over here because lack of space. Let's see if anybody can remind us why we only move one lone pair to form a double bond here. You're gonna end up with a plus charge here, a minus charge here, a minus charge here. Why can't you do this?
It's because periods 1 and 2.
Because nitrogen is in period 2, and only atoms in period 3 and below can have more than 8 electrons on their outer shell, right? So therefore, you cannot do this. So let me erase that here. So therefore, this would be the final Lewis structure for the nitrate ion. Okay. So that's the Lewis structure. Okay, so what's the shape? Trigonal planar. Let me write that down here. Trigonal planar. All right. Okay. And what would be the polarity? Well, let's think about the trigonal planar shape. It's gonna look like this. And because these atoms are identical, these angles are going to be exactly 120 degrees all the way around, right? So what do you think would be the polarity based on this spatial arrangement? If you have a central atom and you have 3 oxygens in one plane, evenly spread out.
Non-polar.
Non-polar, exactly, because these dipole moments will cancel out each other if they're evenly distributed in the same plane. You see what I'm saying? So therefore, this would be a non-polar geometry, non-polar molecule or ion, whatever like that. All right. So basically, that's it for this one. Any questions? You look puzzled.
I'm very puzzled. So all the trigonal shapes are all gonna be non-polar?
If the atoms are identical. No, the central atom.
Okay,
Right.
I guess it was just the way it was right, it's supposed to be, it's like to
Yeah.
even try to point.
Even grants,
All right.
equally spread. Right. Perfect geometry, perfect symmetry.
Okay,
Yeah.
thank you.
Okay, any other questions about this one? Any other question? Okay, let me clear this here. And let's look at the hydrogen ion. Okay, so again, how do we start off this thing here?
Just 1 times 3.
H will give you 1 times 3, which will be 3. And oxygen will give you how many? 6, right? And the plus charge, that means we're gonna minus 1 electron, right? So that's 3 plus 6, 9 minus 1, so that's 8 electrons, which would be equal to 4 pairs. All right, so we put the oxygen in the middle and surround it with the hydrogens. Right, and then we put the bonding pairs first. 1, 2, 3. We have 1 more pair to play with. that goes here, all right? So let's do the formal charges. Formal charge is equal to what? I'm sorry, for the oxygen is equal to what?
Is
Will be what?
6.
6 minus half of
6.
6 minus
Two.
2. So that's 6 minus half of 6, which is 3. 3 minus 2, that gives you +1. So there's a +1 charge on the oxygen, and then we do the same calculation for hydrogen. So that's what? 1 minus half of 2 minus 0, which will give you 0. So there are no charges on the hydrogen. So this is basically the Lewis structure for the hydrogen ion. What's the next step?
Determine the shape.
Okay, so what do you think the shape of this is? Now, in this case, you have an oxygen bonded to 3 hydrogen atoms and has a lone pair here. So what do you think the shape is?
some form of bed.
No,
Tetrahedral.
no,
Trigonal. Trigonal?
no, not trigonal. You have a
Oh,
lone pair here, so it can't be trigonal. Trigonal would be, yeah, 3 bonding pairs.
So we just named all of them.
Nope, you have octahedral, you have, well, the answer for this one is, pyramidal. So that table I'm going to provide you will give you all of that, all right? So if it is pyramidal, let me draw it over here. It's going to look something like this. Right? And you're going to have a lone pair here, right? Now, in this particular case, the oxygen is more electronegative than the hydrogen, right? So therefore, you're going to have one dipole acting in this direction, another dipole acting in that direction, the third dipole is acting in that direction. So what do you think the polarity of this molecule or ion is?
Oh.
Exactly, it's going to be polar. Because they won't cancel each other. Right, so that's basically it as far as the polarity is concerned. All right, now, when submitting this, I would accept if you do this on a separate sheet, because apparently I didn't provide enough space to show all the work, right? So if you want to do it on a separate sheet and submit it that way, I have no problem with that. Okay, yes, ma'am.
So when we're trying to decide if it's is that something that we're using the pictures for, or can we determine that by looking at the charges?
No, you have to think about the 3-dimensional shape of the molecule. And you have to look at the directions, as a result, the direction of the dipole in a 3-dimensional way. And if they cancel out, then the molecule is nonpolar. Like in the case of carbon tetrachloride that we looked at earlier, right? Tetrahedral, let me put it this way. If the molecule is tetrahedral and all the atoms surrounding the central atom are the same, that is definitely a nonpolar molecule because the dipoles will cancel each other. The same is true for the trigonal planar arrangement. In fact, those are the first two that comes to mind when it comes to nonpolar. For most of the others, it's going to be polar because again, you have to look at how the dipoles are arranged in 3 dimensions to see whether or not they'll cancel out each other. Let me see if I can find that chart. Let me clear this first. Okay, I think I have it saved for the interest students. I'm going to show you this chart because you need to be familiar with it in order to I thought I had it here. Um, Alright, here it is, right here. So this chart here, let me just explain. This chart here basically gives you the shapes based on the central atom, the number of bonding pairs or lone pairs surrounding the central atom. So this is a linear arrangement. Now, in this representation, where I introduced you to the to this sort of representation, like AX to E. Well, in this diagram here, the E here is actually the A in our representation, right? And they use dots to represent lone pairs, right? So for example, if you have a central atom here bonded to two other atoms, that's linear, right? If you have a central atom bonded to three other atoms, that's trigonoplanar. But if you have one of these atoms replaced or removed, so you only have a lone pair here, then the angle will be bent or angular. This is the tetrahedral arrangement. And then you have the trigonopyramidal, and then you have the bent, in this case. The angle here will be different here compared to this one here, and so on and so forth, right? So if you, to answer your question, because you're asking, how can you determine, what was it again you asked? How can you determine the polarity, right? Basically you have to look at the three-dimensional shape. So let's say, for example, you're using let's say your molecule has this shape, right? So let's say X is more electronegative than E. That means that you're going to have one dipole acting in this direction, that dipole acting in that direction. These two will cancel out each other, right? But you also have another dipole acting in that direction, right? So in this particular case, this molecule will be polar. Because even though you have these two dipoles canceling out each other, you're still going to have a net dipole of a non-zero value, and therefore the resulting molecule or structure is going to be polar. So these are the things that you look at in order to determine the polarity. Here's another one. In this case here, you only have these two atoms here, linearly opposed. You have lone pairs here. In this case, this will be non-polar because that dipole will cancel out this dipole exactly if these two atoms are the same. All right. So you have to look at each in turn and try to decide whether or not the net result would be that all the dipoles will cancel out. If that's not the case, then your molecule will be a polar molecule. But if all the dipoles cancel out each other, then the molecule or the structure is going to be a non-polar structure or molecule. All right.
That example, why are those poles up and down and not even?
Well, because you have this X here and this X right here. I was assuming that X is more electronegative than the E, right? So if X is more electronegative than the E, that means the dipole for this bond will go from E to X here like that. And the dipole for this bond will go from E to X here like that. And because these two are identical, these two dipoles will be equal to each other, and they will cancel out each other because they are oppositely arranged.
Oh, no, I thought that was for the two on the left side.
Oh, you mean you're talking about this one?
So the top and the bottom would cancel out.
Exactly, right.
But then there's two on the left side and one on the right side.
You mean this? Those are electrons, not atoms.
So that doesn't.
That doesn't, right, okay, I think I know what you're probably confused about. The electron pairs, they don't play any role in terms of the polarity directly. In other words, they do, but at our level, we don't need to concern ourselves with that. The only polarities that you need to be concerned with are the bonds, those shared electrons. The lone pairs do not play any role, or I should say any major role in terms of the polarity emanating from those lone pairs.
I thought that was what Ritzman's meant.
That, right, the lone pairs determine the shape. Right? So basically the lone pairs and the bonding pairs, they will spread out, and therefore based on the resulting three-dimensional arrangement, the shape of the molecule will be determined. But in terms of the polarity here and polarity here, that is only determined by the electrons that are shared between atoms. There's no polarity that would exist here, for example, right? For the lone pair here or here, right? There is some polarity, but it's not really that important at this level. All right. So when you're concerned about the polarities of the different bonds, you're only looking at between shared, you're looking at bonds resulting from shared electrons. That's basically what you look at in order to determine the polarity. Okay, now. Oh shoot, it's 10:44. I was hoping to get to I was hoping to get to the what do you call it? Hybridization. I guess that would have to wait until next time, and then that would be it. Chapter 10 will be it. All right. So you can continue to watch the videos, and maybe you can get a clear picture as to what hybridization is all about, and you can try those questions on your own. But we're going to discuss that, and that will be the last thing that we're going to discuss for this course. All right.
Not doing problem 2 with the,
Oh yeah, problem 2 as well. Yeah.
okay.
Yeah. That has to do with molecular orbitals. Okay, so that's going to be it for today, folks. I'll see you guys. And as I said earlier, some of you may not have been here when I said this. As far as test number 2 is concerned, I'm going to make an announcement about test number 2, because to be perfectly honest, I was kind of disappointed with most of your performances. So I'm going to give you a chance to improve on that. I'm going to post an announcement about that later on today. All right, so look out for that.
Did you finish grading test 2?
Yeah.
Okay, I don't have my grading canvas.
Let me see. Oh, somebody said something in the chat. Oh, yes, to answer Miss Lou's question, there's no lab today, so. I'm going to make myself available next week during lab period, because to catch up on grading on some of your remaining experiments. So you can come by and collect your lab reports next week during the lab period, or actually next week during any of my office hours, but including the lab period. Okay, so Miss, what's your last name again?
My last name is Ben Hartwell. For some reason, the testing center has it under here.
I remember that.
Yes.
Let me check something here. And you know what? That could be the issue again this time around.
That would surprise.
Well, let me check here. But that was an issue. Remember, we were,
I was married last semester and it wasn't an issue last semester. I don't know why it's a problem now.
let me see here. So Miss Bethencourt. Okay, I'm going to run that down again.
Okay.
Yeah, I strongly suspect that's going to be the issue again.
And then I got my test 2, but I still don't have my test 1 graded, was the only thing I was gonna ask you about, because I had them send
It's my
you.
nickname.
What's that?
Test, a brown.
And so it changed.
Agents.
Last semester, the last name
This-
was under Vet Credit Testing Center. For this, I guess so.
Oh, you know what? I have it. I saw it
Then with this.
yesterday on my desk.
Okay,
So I don't know why I did it, but it will be done.
all right, thank you.
I remember seeing it. Yeah, her situation was. I had to go between her and. The testing center.
Sorry. I don't know why, like I was married last semester, was like, I don't know why it wasn't a problem in Charter Chem.
Oh, really?
Yeah,
I don't know.
I don't know. Thank you.
If we did good on the last test, do we get to keep our grade?
Sorry.
If I did good on the last test, do I get to keep my grade?
Oh, yeah. In fact, there are only 2 students who did well. So you guys might not want to be concerned about, the announcement I'm going to make later on. So. Okay, so you guys out there in Zoom, I'll be signing off. I'll see you guys next week.